So far in our study of reactions, we've concentrated on chemical reactions. And chemical reactions involve the valence electrons of the atom. And those electrons are involved in bonding. In a chemical reactions, the bonds of the reactants are broken, the atoms are rearranged, and new bonds are formed to form the new compounds. In a chemical reaction, the identity, or what the atom is, does not change. Here's an example of a chemical equation. And looking at a chemical equation, it will look familiar at this point in the course. We notice that we have the same number of each type of element on both sides of the equation, making it a balanced chemical equation. What we also notice is that the reactants have different formulas than the products, because the atoms have rearranged to form something new. Now, nuclear reactions, while are not quite as common, are very important reactions. We find lots of applications for nuclear reactions. For example, nuclear medicine, where we diagnose and treat a variety of illnesses. We also can generate energy in nuclear power plants using a nuclear reaction. And archaeological objects, we can use isotopes that are radioactive to help determine the date of the objects. In nuclear reactions, as its name might imply, it involves changes in the nucleus. Recall that the nucleus of the atom contains both protons and neutrons. The protons are what give the identity to the atom. So if the number of protons change, then the identity of the atom will change. In a nuclear reaction, radioactivity is emitted or given off, and in many cases, that emission of the radioactivity will change the identity of the element. The change of the identity of the element is known as transmutation. Now, nuclear reactions have a formula that might look something like this. So notice in this nuclear reaction that they're written in isotopic notation. We'll review that in the next slide. Also notice that the elements are not the same on both sides of the reaction, that you have uranium on the reactant side and helium and thorium on the product side. That's a part of the transmutation. The other thing you may notice in doing this type of nuclear reactions is that it involves many of the elements in the belly or the bottom of the periodic table. While a lot of different elements have radioactive isotopes, not all atoms do. Let's review isotope notation. We had done this earlier in the course. So in a general form, we have the element symbol. The element symbol we can find on the periodic table. As a superscript, we have the mass number. Recall that the mass number is not found on the periodic table. The mass number is equal to the number of protons and the number of neutrons. As a subscript, we have the atomic number. The atomic number is found on the periodic table. And we know that the element symbol and the atomic number are related to each other. So let's take a look at how these two, all of these come together. So here we have strontium, and then the dash. This is not a subtraction, it's a dash 85. This is a common way for them to tell us or show us what isotope we're working with. The 85 here they're giving us is the mass number, because remember we can't find that on the periodic table. So I have the 85 as the mass number. That goes up here at the superscript. Now strontium, you may have to look on the periodic table, but on the periodic table you would see that the element symbol for strontium is Sr. So that shows up right here. And then again, referring to the periodic table, you will have the element number, or the atomic number, is 38. So both the element symbol and the atomic number are found on the periodic table. In this chapter, it's probably be very helpful to have a periodic table close by. Let's look at a second example and try to put it together. So here we have cobalt 60. So again, 60 is the mass number, so you see that it goes here as a superscript. Cobalt has a symbol of CO as found on the periodic table. If you find cobalt on the periodic table, you will see that its atomic number is 27. So get out a periodic table, have it nearby, and let's go ahead and look at these two and see if we can come up, both gallium-67 and selenium-75. Let's come up with a variety of information that we can get from that name and number. So gallium-67. If you look up gallium on the periodic table, you will see that its symbol is Ga. And finding Ga on the periodic table, you see that it has an atomic number of 31. So its atomic number is 31. The atomic number is also the number of protons, so I can put 31 right here. Now the mass number is determined by this number right here. We can't find the mass number on the periodic table, so it's given. So the mass number is 67. Now mass number equals protons plus neutrons. So if I take the mass number and I subtract the number of protons, this is protons, this is the mass number, then I would get the number of neutrons. So there's 36 neutrons. So the isotope symbol, we have Ga for the element symbol. The mass number is 67, and the atomic number is 31. So now let's try this for selenium. And you can always pause and try to fill it out yourself before I go. So again, here's the name of it, selenium-75. This is just a dash. So if I look up selenium on the periodic table, and its symbol is Se. So looking up selenium, I see that it is element number 34. That's its atomic number. The atomic number is the same as the number of protons. The mass number is given by what they showed us here as 75. The mass number is equal to the protons plus the neutrons. So if I take the mass number and subtract the number of neutrons, the remaining must be if I take the mass number and subtract the number of protons, then I get the number of neutrons. So that's 41. So then the isotope symbol, I put the symbol of the element Se, the mass number 75, and the atomic number on the bottom 34. Review your isotopic notation before you proceed further.